Okay, hello everybody. Welcome to lecture 18. It's week 10 of lectures and everyone is very welcome. So at this point we've completed our first two chapters of the curriculum. First chapter on integration, second chapter on sets of real numbers and sort of concepts of infinity and dealing with infinite sets. So the third chapter is about sequences, series and convergence. And it relates, I suppose, more to the content of chapter 2 than to the content of chapter 1, although we will see some connections there too. And it's sort of something of a clean break after chapter 2, although we will be using some of the ideas that we met in chapter 2. And so just in order to motivate this topic, I wanted to start with a few examples. I think this is a subject, convergence, which is one, it's extremely important in mathematics generally, but it's something that when you first meet it, it can be quite easy to kind of not, wonder why is this important, what's it about, and indeed it can be quite easy also to neglect to discuss that particular issue. So what I have here in these first examples in section 3.1, which is really just an introduction, is just a few examples that I hope might sort of be helpful in convincing us that this is actually something worth looking at and something that's important. So we're not really going to worry too much in these first examples about kind of formal definitions of convergence. We're just going to look and see sort of what it might mean in practical terms, and then we'll formalize it a bit more as we proceed, because as always in mathematics we need very precise definitions so that we can have clarity about what it is that we're talking about and what it is that we're reasoning about. Okay, so first question. We've been talking about infinity and we've been talking about infinite sets, and obviously we're doing mathematics, so we like to work with numbers, for example, and we like to do arithmetic operations with them. So here's a question. And the question is, I guess there are two purposes here. One is to mention this notation in case not everyone's familiar with it, and second is to just ask this question. Does it make sense to talk about this number? And the number, basically, if you look at the right-hand side of the equation there, is the number 1 plus 1/4 plus 1/9 plus 1/16 plus 1 over 25 plus ... And of course, there's already a bit of a lack of precision there in what the ... means, but hopefully we can sort of extrapolate from what's written and say, well, the next term there should be 1 over 36 and then plus 1 over 49 and so on. So what this thing is it's a sum of reciprocals of squares, 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, and so on. But it goes on, like it doesn't stop anywhere. And so the notation on the left-hand side here is a shorthand and compact and convenient notation for the same thing. So this means the sum of the expression 1 over n squared. Okay, the 1 over n squared is the bit that comes after this thing is a capital letter, capital sigma. It's used for sums, infinite or finite sums. So this means the sum of the expression 1 over n squared as n goes from 1, which is the lower subscript here on the summation sign, to infinity. And okay, it doesn't actually say that n goes from 1 to infinity in steps of 1, but that would be interpreted, that would be considered to be implicit in that notation there. So n going from 1 to infinity means for n equals 1, n equals 2, n equals 3, and so on. Again, if that's sort of generally sort of implicit in the notation there. If it isn't clear from the context, it would have to be stated what the steps are for n. Okay, so that's what this thing on the left means, and the capital sigma there, this is referred to often as the summation sign. And it's a handy one to have in your vocabulary, or your whatever you call the written version of a vocabulary. So and yeah, so I mean, it relates actually to the integral sign, as we mentioned back in chapter 1, that the integral sign is kind of a limit of this thing, as this intervals that you're summing over become infinitesimally small. Okay, so that's the question. Does it make sense to talk about that number? Okay, a number is there in quotes because it's not really clear if this thing is a number or not. So what can you do with it? So obviously, like you can't perform the task of adding together infinitely many numbers by a sort of usual addition process like we'd use for a finite collection of numbers that we want to add together. So it's not like asking, does it make sense to talk about the number 1 plus 2 plus 3 plus 4? Obviously it does, and we can all add those numbers up in our head. But the point is here, we've got an infinite number of things to add together. So we can't just, we can't just add them up. So does this expression, this infinite sum, have an interpretation as a number that makes sense? That's kind of the question. And so I suppose you could think of this as being related to the question, can you add together infinitely many numbers? What would it mean? What would the answer be? Okay, well, okay, what can we do with this? Well, one thing that we can do, I mean, it's a sum with numbers written from left to right. The first thing there is 1, the next one is a quarter, and so on. So we can add together the first 2 terms, and we get 1.25. Okay, so that's not controversial, I guess. We would have done that anyway. We can add together the first 4 terms, for example. This is the second point. And if we did that, we would get 1.4236. Okay, fine, we can do that. We can add together the first 10 terms, maybe up as far as 1 over 10 squared. And if we did that, again, so any of these things we can do, you know, whether we can, you know, whether there's a quick way to do them or whether we have to just do all the addition is another question, but in principle, certainly we can do these things. If we add up the first 10 terms, up as far as 1 over 10 squared, we get 1.549. Okay, so this number is growing. It's growing not terribly fast, and of course that shouldn't surprise us, because as we travel further out along the infinite sum here, the bits that you're adding on are like 1 over n squared for values of n that are increasing. So the bits that are being sort of added on at each step are certainly getting closer to 0 as we proceed. So we shouldn't be surprised to see that, you know, the sum, the total, doesn't increase that much as we proceed. So for example, when you go from 4 terms to 10 terms, from line 2 to line 3 here, the sum goes from 1.42 to 1.55 or so. So it increases by more than 0.1. When you go from taking the first 10 terms to the first 200 terms, you add about another 0.1 or so onto the total. When you add on another 10,000 terms, from the first 200 to the first 10,000, you only add on about 0.01 onto the sum. And then the last one that's listed there is 100,000 terms. So when you go from 10,000 terms to 100,000 terms of this sum, if you believe me, the total doesn't actually increase very much at all. It only increases by something like 0.0001. So, okay, so like looking at these numbers, it looks like the further out you go, the less it changes the total, which again is not a very precise statement. And neither is it a very hugely surprising one when you consider that what you're adding on at each step is just like 1 over some giant number. So it's something very close to 0. But on the other hand, like going from step 5 to step 6 here, we've added on, what have we added on? We've gone from like 10,000 terms to 100,000 terms. So we've added on another 90,000 terms. And the effect of that has only been to increase the total by about 0.0001 or something like that. Okay, and the other thing we can observe, I suppose, is that, you know, as we keep going, it seems to be sort of maybe settling down and not increasing too much more. It's something like around something whose first 4 digits after the decimal point are something like 6449, so something like 1.6449. After 100,000 terms, we have 1.644924. Okay, fine. This is numerology. I mean, what can we say about it? Well, observation out of the blue is that the number pi squared over 6, if you believe this, looks very like that. It's not quite the same, but in the first 6 places of decimals, it looks very like it. It's 1.644934 plus. I should. It's obviously more decimal places after that, because pi squared over 6 is not a irrational number. But okay, so is it a coincidence that when you add up the reciprocals of the squares, the reciprocals of 1, 4, 9, 16, and so on, I keep going and keep going, that as you keep going further and further out, you seem to be sort of getting close to this number, pi squared over 6? Or is it just a sort of fluke, or is it a sleight of hand to do with where I stopped counting in this particular example? Is there something going on here or not? Okay, that's kind of a question, and we're not going to answer it immediately, but it's the sort of question that the content of this chapter might be able to sort of answer. Okay, so the series, this is an example of what they call an infinite series. We'll have a precise definition later, but a series is basically the sum of infinitely many terms. Okay, that's what a series is, where you have a first term, a second term, a third term, and so on, and you sort of try to add them all up. That's a series. Okay, and the assertion is that the series, sum of 1 over n squared, and going through the integers, starting at 1, the positive integers, converges, that's a word that might be new for us, and it's a word that we'll be seeing a lot in the next couple of weeks, converges to the number pi squared over 6. Okay, so I haven't given precise definitions for any of these terms, so you know, if you'd like one, it's coming shortly. But basically it means that when we keep adding on more and more terms to this series, more and more terms of this infinite sum, we keep getting nearer, or we get nearer to pi squared over 6. Okay, and of course, get nearer is another vague phrase which I'll be trying to pin down a bit later in terms of precisely what it means. But that is what happens. And I think, to me at least, thinking about examples like this, we're going to be looking at a lot of examples about sequences and series, and it's sort of, as with the integration in chapter 1, it's very easy to get you're kind of preoccupied with examples and to kind of forget what the big picture is. And so to me, I think this is an example I would keep coming back to if I was wondering why are we doing this? This is kind of a remarkable fact. There's certainly pi. Why is pi important? Well, pi is the ratio of the circumference of a circle to its diameter. So there's certainly, I think, no obvious connection between the number pi and squares of the form 1 over n squared, 1/4, 1/9, 1/16, and so on. Another remark is that all the terms in this series, 1 over n squared, they're all rational numbers. They're all quite nice rational numbers. They're fractions with numerator 1. So all the terms there are rational, but pi squared over 6 is definitely not rational. And the other final remark about it is, okay, this is another observation, that this example gives us, in principle at least, a way of calculating the digits of pi, or at least of pi squared over 6. So, if you want to estimate the digits of pi squared over 6, and if you believe what I've just said, which you have no strong reason to believe right now, apart from the partial additions of this series in the previous slide. But if you did believe it, then it would give us, in principle, a way of calculating the digits of pi squared. And that's another interesting thing, I think, because, of course, we all know that pi is a number that has a infinite decimal representation, which has no repetition and it doesn't terminate. And people sometimes like to write down lots of digits of pi, and some people even kind of have a hobby of memorizing lots of digits of pi. But how do we know them? And how does one actually go about trying to calculate them? And it doesn't really come from the geometry of the circle, because the circle geometry, although it has loads and loads of interesting and beautiful things about it, doesn't give us a way of calculating this actual ratio of the circumference to the diameter of a circle. There are experiments that you can do using sort of probabilistic methods that relate to that, and that can be used to calculate digits of pi. But another way to do it, and the way that it usually really is done, is by using these kind of series representations of pi, by representing pi or numbers like it as somehow sums of infinite series. And the theory of why this thing actually converges to pi is accessible, although we're not going to cite it right now. Okay, so that's another remark that, a reason why it's not only interesting but also useful to look at these sort of infinite series is because it enables us to calculate things that we might not be able to calculate so easily otherwise, even though we're kind of used to them, because we have obviously computers at our disposal and everything, and we know that we can look up the digits of pi, and it's easy to not ask ourselves, how are these things actually calculated? Well, this is the kind of way that they are calculated. Okay, so that's the first example, and and I guess one thing to notice about that example is that the terms of this series, as we add them together, they're getting closer to 0 all the time. So, for example, like we have 1 over 25, then 1 over 36, 1 over 49, and so on, and they're rapidly approaching 0. So that, I guess, gives us it gives at least some plausibility to the idea that when you keep adding more and more terms onto this sum, that maybe the total doesn't increase without bound, because the things you're adding on maybe are very tiny, and they're shrinking even faster than the sum is growing somehow, so that the number the total might settle down to some numerical value rather than increasing without bound. So like if we were to ask the same question about, the number 1 plus 1 plus 1 plus 1 plus 1 infinitely many times, then the answer is, well, that certainly is not a number, whatever it is, because if you keep adding 1, you just keep increasing without bound. But if the terms of the things that you're adding on are heading towards 0, then potentially the sum could actually head towards some value that is not infinite. Okay, so this is a case where it does happen, although that's not obvious except by this numerical experiment, which gives it some credence, but maybe doesn't prove it. Okay, right, so that's the first example. All these examples are in the lecture notes as well, of course. Okay, second example. This is an important and sort of classical one that has an important role in the development of this subject. So, and it's kind of an obvious one maybe as well to look at. So the kind of position now is that maybe if you're looking at a sequence of terms that are approaching 0, where the individual terms are approaching 0, then potentially maybe you can give a numerical value to the sum of these infinitely many terms. So an example of that, which is sort of reasonably obvious one, I guess, is if you take just the reciprocals of the integers themselves, the positive integers. So in the last example, we looked at the squares of the positive integers, which are certainly approaching 0 a lot faster than the reciprocals themselves are. So if you just look at 1 plus a half plus a third plus a quarter plus a fifth plus a sixth. Okay, so again, that's an infinite sum. And again, you can do what we did before. You can add together sort of initial chunks, initial segments of this infinite sum, and you can look at the behavior of the total as you keep doing that. In the previous example, we sort of saw, at least again, I'm kind of asking for your indulgence here, I guess, in sort of believing me, and also in believing that this is somehow convincing that, you know, when you go even like from the sum of 10 terms in the first example to the sum of 10,000, 100,000 terms, that the difference in the total is only like, it's a 0.1 or so. And so, you know, that's a lot of terms to add on for a small increase in the total. And so it doesn't prove that the series is converging to what we said, but it kind of maybe supports that assertion. Sorry, I'm flicking around here. So if you do the same thing with this series 1 over n, so 1 plus a half plus a third plus a quarter, what's been added on at the nth step here is 1 over n, not 1 over n squared, so it's approaching 0, but not as fast. And again here, if you experiment with initial segments, so I mean, I did this with a computer, of course, I didn't do it by hand, but if you take the first 50 terms, 1 plus a half up as far as 1 over 50, what you get, rounded off to 4 places of decimals, is something like 4.4992. If you do it for 100 steps, it increases from that, 4.5 roughly, to about 5.2. So from step 51 to step 100, what you add on is about 0.7. If you go up as far as 1,000 steps, you get an increase, like it goes from 5.2 to 7.5, more or less, by adding on another 900 terms. If you add on another 49,000 terms by going from the first 1,000 terms to the first 50,000 terms, then you add on something like about 4. So it goes from 7.5 to about 11.4. Okay, so here again, okay, I mean, there's not a lot that we can read here because we're adding on a lot of terms in each of these 4 bullet points. But we can't say, at least from this amount of observation, that it's definitely sort of, or that it appears to be convincingly sort of converging to something that we can recognize. You know, admittedly, we had to add on 49,000 terms to go from 7.5 to 11.4, but we did it. So there's no knowing that it wouldn't, if you add on another 5 million terms, that you couldn't get up to 20 or something. Okay, so at least from this amount of evidence, we can't really say that there's anything convincing suggesting that this is maybe converging to something. If it is, it's not really visible from these observations, which, you know, the previous case, I guess I'm not saying that anything has been proved, but it's a bit more convincing, you know, when you go from 200 terms to 100,000 in the first example, you're still sort of at 1.64. You haven't really progressed much beyond that. So here, it's different from that. Okay, so can we say anything here about whether this infinite sum, 1 plus a half plus a third plus a quarter, has a value or not, a numerical value or not? Well, not from this evidence really, I think. So we'll come back to this one. This is called the harmonic series, and it's an important one in the whole theory about convergent series. So let me just remark, in case anybody wants to think about this, and we will. Oops, sorry. We will come back to it. That here's a little task for you to think about if you want to. So if you want to just think about this in another way, I think it was section 1.5, certainly the last section of chapter 1. From section 1.5, that if you take a kind of related thing, the improper integral from 1 to infinity of 1 over x. Okay, how is this related? Well, that's for you to think about at the moment. We will revisit it. We saw in chapter 1 that improper integral is divergent. Okay, so it's an integral of 1 over x, not the same thing as a sum of 1 over n, but there is a connection between them, which you could think about if you want to, by looking at the area that improper integral represents. And we saw back in chapter 1, on our work on improper integrals, that the area enclosed by that integral under the curve 1 over x from 1 to infinity, that area is actually infinite. Okay, and that area somehow can be related to the sum 1 plus 1/2 plus a third plus a quarter plus a fifth. It's not the same thing, but we can relate them in a way that would allow us to see that if one of them is infinite, maybe the other one is as well. So I'm going to leave that for you to think about for the moment, and we're going to revisit it in a later section of this chapter. But if you're interested, it's worth thinking about that maybe in advance. Okay. If anyone has a question, please feel free to turn on the mic or to put a question in the chat. Just pause there for a second. Okay, well, here's another example. And again, this sort of looks a bit like the others, but it's a bit different in what happens with it. So this one is 1 over the sum of 1 over the even powers of 2. So we've looked at the reciprocal of all the squares. That seems to be something like pi squared over 6. We've looked at the reciprocal of all the natural numbers themselves, 1 over n, that have a sum that we could quickly recognize. And now we're looking at the sum of the reciprocals of the even powers of 2. So 1 over 4, 1 over 16, 1 over 2 squared, 1 over 2 to the 4th, 1 over 2 to the 6th, and so on. Okay, so again, experiment with a few initial pieces of the infinite sum. And this kind of experimenting, I mean, it doesn't really sort of prove anything, but I think it is quite useful for giving us a sense of what's going on here, what this topic is about, and what kind of different behaviors these kinds of series can have. So if you take the first 2 terms, 1/4 plus 1/16, okay, we can alter that one, that's 5 over 16. Great. If you take the first 5 terms, so 1 over 2 squared, 1 over 2 to the 4th, 2 to the 6th, and so on, up as far as 1 over 2 to the 10, what you get is 341 over 1024, which is 2 to the 10. And that's 0.333 something. So that's a number that we can all recognize, of course, the 0.333 part anyway. If you go up as far as the first 7 terms, so 1 over 2 to the 2, 1 over 2 to the 4, up as far as 1 over 2 to the 2 times 7, what you get there is 0.3333, correct 4 places of decimals. And you can sort of guess what happens if you go a bit further. And indeed, I invite you to do that if you're interested in having a look, or if you're unconvinced so far. So, okay, so these calculations we will verify directly later using geometric progressions, but it certainly looks like this series is converging to 1/3, that if you add on more terms, you get it looks more and more like 0.33333. Okay, so what are we looking at here? 1 over the reciprocal of even powers of 2, starting with a quarter. So here's another way that we could look at this. So this picture is here for interest. It's just, I suppose, to suggest maybe that sometimes there can be more than one way of looking at these things. So this picture is supposed to sort of justify the assertion that maybe this infinite sum is 1/3. And okay, so we're talking about a quarter plus 1/16 plus 1/64, and so on. So this picture, if we imagine this square to have side length 1, the big square, and it's kind of broken up in a particular way, and parts of it are colored red. So I suppose the suggestion here is the red square here. The first kind of big red square there in the lower left kind of corner, the big square is assumed to have side length 1, so the total area of the big square is 1. And the red square there, its area is 1/4 of the total area, which is 1/4 because the total area is 1. So it's like that square is 1/4 of the whole thing. And I suppose if you look at the way that the square is kind of broken up in this picture, so let me find a color. So this, if we think about it as being broken up into sort of L shapes like this, so this is one of them, like consisting of all of it except the lower left square. So if we look at that, then we can observe that this thing that's outlined in green is 3/4 of the total, but also the part of it that's colored red is 1/3 of that part. Okay, so let me maybe write something just in case you're looking at this later and wondering how you were supposed to interpret it. So the lower left red square is 1/3 of the green, of the L shape that's outlined in green. Okay, which is incidentally 3/4 of the total, but we don't need that so much. I mean, the point really is that the whole thing kind of breaks up into a bunch of these L shapes. There's another one here. And part of that is colored red as well, which is 1/3 of it. But that part is 1/4 of the square on the top right, which is 1/4 of the total. So its area is 1/4 of 1/4. The purple square, or sorry, the top right square is 1/4 of the total. And the part of that that's red, the lower left red part of that is 1/4 of that. So it's 1/16 of the total, but it's 1/3 of the purple part, and so on. So basically what we're saying is the next bit, this, let me find another color and then I will soon stop this because I'm going to run out of colors and make a total mess of it. Anyway, so this bit, okay, that's 1/4 of 1/4. So it's 1/16 of the total. And the lower left red part of that is 1/64 of the total because it's 1/4 of 1/16, but it's also 1/3 of the sort of L-shaped piece in which it's contained. So basically the entire picture is a union of these disjoint L things that don't intersect each other. And the part that's covered in red is consists of parts, each of which is 1/3 of one of those L's. So 1/3 of the entire picture is colored red, okay, because it's 1/3 of each of these L's, and the L's fill up the whole picture. So the squares that are colored red account for 1/3 of the entire picture. But they also, when you actually count their areas, it's 1/4 plus 1/16 plus 1/64 plus 1/256 and so on. So it's actually exactly this infinite sum that we have. Okay, so the red square is basically their total area is 1/4 plus 1/16 plus 1/64 plus and so on. But by interpreting the picture in terms of these sort of L shapes, we can see that it's actually that their total area accounts for 1/3 of the entire area of the unit square, which is area 1. So the sum of those individual areas, 1/4, 1/16, 1/64, and so on, should be 1/3. So it's just, I think it's just an example to show that sometimes you can give a kind of a visual interpretation to these things. Sorry. Okay, so that's another sort of nice example, in my opinion, at least. And sometimes these visual interpretations can be quite convincing. Another remark, I suppose, about this example is that in the first case we had a sequence of, or a series of rational numbers, 1/n², and their sum seems to be something like pi²/6, which is definitely not rational. In this example, we've got a bunch of rational numbers, 1/2 to the power of some even integer, which are certainly rational as well, very nice fractions, 1 in the numerator, powers of 2 in the denominator. And they, again, this seems to be a convergent series. What it's convergent to in this case seems to be 1/3, which is rational. So certainly, you can have a bunch of rational numbers whose infinite sum is rational. It can also be irrational, as we had in the first example. And I suppose we're kind of interested potentially in all these possibilities. Okay, anybody have a comment or question? Okay, we have one more example. And this is a different type of example. And again, I suppose the assertion for the reason for mentioning this and the is the claim that it's something that's actually useful. So, question, and this is again, when you first look at this, the question is, does it make sense to talk about this thing and think of it as a function of x? Why would anyone ask that question? I think is the first thing that I would say if I were presented with it out of the blue, and if I hadn't already sort of known about know the answer to that. So, but if you suspend your skepticism there about that for a second, the question is, can we take something like this, define a function of x? So we're all very used to dealing with polynomial functions of x, and things like x to the 5 plus x to the 4th plus 3x² minus 1/4 x or whatever. And there are lots of reasons why polynomial functions are really nice functions. They're really easy to deal with in calculus, for example. They're not always easy to deal with in terms of solving equations, but in terms of their, the objects of calculus, they behave quite nicely. And they're also very good for approximating things that are more complicated than themselves. So there are lots of reasons to be interested in polynomials. The question here is, could you have sort of like an infinite polynomial? A polynomial with infinitely many terms. So, and the particular example that's given here is presented, you might ask, well, why that one? But here we have a polynomial sort of in inverted commas, with the term x, an x term with coefficient 1, an x cubed term with coefficient 1 over 3 factorial, which is 1 over 6. Next to the fifth term with coefficient 1 over 5 factorial, and so on. Remember, factorials, I know that you know this, but just in case anyone's temporarily forgotten it. 5 factorial means 5 times 4 times 3 times 2 times 1. So it's the product of the numbers up to 5, and so on for the others. So, you know, it doesn't make sense to kind of write down an expression like that. And of course you can write it down. You can write anything down, but that doesn't have meaning as a mathematical object. Can we think of it as a function of x? So this is a step removed again from just asking, can we have an infinite sum of numbers? If this thing makes sense as a function of x, it would mean that we'd have to be able to plug in a value of x into it, like maybe x equals 1 or x equals 25 or whatever. And then we'd get an infinite sum of numbers. And would we be able to give a value to that sum? Would it be a number? Would the infinite sum sort of converge in the way that we've been talking about, at least for some values of x? Okay, so basically, can we plug in values of x in there and get numbers as the result? Is that something that makes sense? Okay, so again, not obvious yet why we would want to know. Why we'd want to do this. It seems to be a sort of very complicated thing to do with a function that might not have been so bad in the first place. But if it does, then f would have to have a domain consisting of some real numbers, or maybe all real numbers if things were good. And substituting these values in the domain into the definition, which is this infinite thing, would have to make sense. It would have to give us some kind of values. Okay, so well, let's try it for some values of x. So if you put x equals 0 into this example, well, that actually is fine, because every term in that infinite sum then evaluates to 0 if you put x equals 0. So we have a bunch of zeros and we can add them up and get 0. So that one is all right, even though it's a complicated way to say that 0 equals 0. But yes, so then if this thing is a function of x, then its value at 0 would be 0. If you put x equal to pi over 2, and again, like why am I picking pi over 2 as opposed to all of the other things you could pick, would be a fair question. But if you do it, then curiously, you get an answer that's nice. After taking 6 terms of putting the value x equals pi over 2 into this thing. So that would be up as far as, so there are odd powers of x appearing there. So the first 4 are here. The 6th one would be minus x to the 11 over 11 factorial. And I claim that if you do that for 6 terms with x equal to pi over 2, you get 0.9999. Okay, well, that's a nice number. If you put x equal to pi over 6, and again take 6 terms, you get something that the first 4 places of decimals agrees with 1/2. And if you put x equals pi over 3, again, why would I pick pi over 3? Well, after 6 terms, you get something that agrees to 4 places of decimals with the square root of 3 over 2. And so in all of these cases, at least, and you know, if you don't believe those particular assertions from me, you can check those all right, because we're only talking about 6 terms. So even with the calculator, you can check that I'm not making this up. In all cases, we get, just from the first 6 terms, something that looks like sine of x, for these values of x at least. Okay, and I suppose the reason why I picked those values of x is because they are values of x for which the sine function has nice values that we can recognize. Okay, in general, of course, if you put a nice number into the sine function, you don't get a nice number out. And by nice, I mean like an integer or something. But if you put kind of nice rational multiples of pi in there, you do get sometimes recognizable things coming out. So, in fact, this infinite series does represent the sine function in the sense that if you put any real number in there, you'll get a convergent series. And what it converges to would be the value of the sine of that function, which might seem kind of like a curiosity until you think about, well, how do we actually know what the sine of any number is? So like, if I want to know what the sine of 2 is, the definition of it is, and here, I know that we all learned about sine and cosines initially in terms of right-angled triangles, but that's not really how the sine and cosine functions are defined. And the domain of the sine function is not a bunch of angles and triangles. It's the real numbers. Okay, this is a very bad picture of the unit circle. But okay, so if you want to know what the sine of pi over 4 is, or pi over 2, or 0, or pi, that's easy because they are sort of recognizable, readable coordinates on the unit circle. And you can use the geometry of triangles and whatever to figure out what the sine of pi over 3 is. But if I want to know what the sine of 2 is, okay, what can I do? So the definition of the sine of 2 is, so what's the meaning of sine of the number 2? Well, it's the y coordinate of the point that you get by starting at the point 1, 0 and traveling a distance of 2 around the circumference of the unit circle. So the unit circle has diameter 2, so its circumference is 3 pi, which is 2 pi, which is about 6. So 2 is like roughly about a third of the way around. So I travel from 1, 0, a distance of 2 around the circumference of the unit circle. And the point that I reach, its coordinates are the cosine of 2 and the sine of 2. That's the definition of the cosine and sine functions. And you can do it for any real number. If the number you pick is bigger than 2 pi, you'll be doing some laps around, but you can keep traveling until you've traveled that distance. And you can look at where you are, and the coordinates of that point are the cosine and sine of 2. And if your number is negative, you go in the other direction. That's how the cosine and sine functions are defined. But that's great. Like, that's absolutely fine. We can, as a conceptual description of a function, it's perfectly good. But if I actually want to calculate the cosine of 2 or the sine of 2, what I know is I have this arc length of 2 in the unit circle, and I have a radius of 1. So like the geometry for calculating the coordinate of this point is not so straightforward. So if you actually want to calculate the sine of 2, this is how we do it. And that's how computers do it. And that's how we have values of when I was in school, calculators were not as advanced as they are now. We actually had a table of values of sines. And that, so it was just like, it looked like the statistical tables that you look at, just pages full of tables. It was a precursor to the modern formulas and tables book that the people use in the living cert. And it had tables of values of sines and cosines, and also of squares and square roots and things like that. And yeah, where you get these numbers from is essentially from these kind of infinite series representations. It's not from the geometric definitions of trigonometric functions, for instance. And so, so yeah, that's if you want to know what sine of 2 is, put x equals 2 in here, and that's more than likely how a calculator does it, or how a computer program does it. So okay, that's so I suppose the punchline there is that this kind of concept of series representation of functions is something that's really valuable. It's not always in the foreground when we're working with functions because of the technology that's available to us, but it's actually how we're able to evaluate these functions, which have definitions like this, which make total sense in terms of geometry, but are not so convenient in terms of actually calculating their values. The fact that these functions also have representations as power series, this is called a power series, we'll meet that formally a bit later, is something that's really, really, really useful. And so certainly people are still interested in finding good representations for functions that they want to work with in lots and lots of applications and in things like that. Okay, that is the introduction to this chapter. So these are the themes we'll be working with. I suppose the general tenor will be kind of not as abstract as chapter 2, where we were talking about kind of philosophical concepts almost about numbers. Here we will have our feet a bit more on the ground, but we're still dealing with concepts like convergence and the notion of adding together infinitely many things. So there's still a sort of strong conceptual element. Does anybody have a question or a comment right at this moment? If you do, please feel free to put one in the chat or to turn on your microphone and ask it. Okay, that was section 3.1, and I guess I hope you found it interesting. I think those examples are interesting, and I guess what it's there for really is to kind of flag some of the themes that we'll be looking at and why they're of interest. So we're going to have to, of course, give ourselves a few kind of more formal definitions so that we can work with these concepts, and that's really the content of section 3.2. And we're going to build up a little bit from here. From the idea of a sequence to the idea of a series and an infinite sum. And so we do need a few definitions. So I guess what section 3.1 is sort of there for, maybe, if it's useful, I don't have specific learning outcomes for it, is just to kind of remind yourself of kind of what the sort of slightly bigger picture is when we're looking at definitions relating to sequences. So let me maybe take another 5 minutes just to introduce some of these ideas that we'll develop a little bit more tomorrow in section 3.2. So this is sort of the formal content that will enable us to make a bit more sense of the examples that we've seen in the first section there. And just to remark that if you like Stewart's calculus, chapter 11 of that is a reasonable, I think, reference for this stuff. Also, the lecture notes, I hope, are reasonably complete. But if you like to have a book to look at as well and some examples there, Stewart's calculus does look at this material in chapter 11. So, okay, so a sequence is an infinite ordered list. So A1, A2, A3, and so on. So the dots are supposed to indicate that this goes on forever and that there's an A for each natural number. That's what it is. It's an infinite list. It has a first term, a second term, a third term. So it's different from an infinite set in the sense that its terms are ordered. There's a first one, a second one, a third one, and also in the sense that it's different also from an infinite set in the sense that it can have repeated terms, like A1 and A2 can be the same. Okay, so the items in a sequence, this is just language. The items in the list are called terms. That's just the lingo. You call them terms. And in our context, the terms in a sequence will generally be real numbers, but they don't have to be. A sequence can have, the terms of a sequence can be anything at all. They can be people's names, or they can be anything, whatever. But for us, they'll be real numbers. Okay. And so a bit of a notation. It's typical to denote a sequence whose terms are called A1, A2, etc., by this kind of AN with round brackets around it. And again, this is yet another example of a use of round brackets in mathematics. That they have so many uses. But I suppose the thing that I sort of suggest connecting this to here is using round brackets for a sequence, in a sense, is kind of consistent with using round brackets for ordered pairs of numbers. So, you know, for example, if you write 1, 2, of course, that can mean the open interval 1, 2, but it can also indicate the ordered pair 1, 2. So ordered means there's a first and a second element. So, you know, that represents the point whose x coordinate is 1 and whose y coordinate is 2. And, you know, what I mean by ordered pair is that as opposed to, if you put curly brackets around the 1 and the 2, that just means the set whose elements are 1 and 2. But neither of them is designated as the first or the second element, so it doesn't represent you know, a point in the plane, because it's just the set whose elements are 1 and 2. So I suppose the remark there is just the use of round brackets here is sort of consistent with the use of round brackets for finite lists to indicate that we care about the order in which the elements are represented. So, you know, the ordered pair 1, 2 in round brackets is different from the ordered pair 2, 1. But if you put curly brackets around them, it doesn't matter which one you write first. It's just the set whose elements are 1 and 2. So yeah, the point there is just to mention that this use of round brackets is sort of consistent with other uses of round brackets to indicate that order matters. Sometimes if you care about where the indexing starts, you might put that the sequence starts with n equals 1 and goes to infinity or whatever. You know, it might start with A0 or A2. But if you want to emphasize that, you can sort of write it like that as a decoration on the name of the sequence. Okay, so generally, so a sequence can be, as I said, absolutely any list of numbers. There might be an overall formula that tells us what the nth term is. So in our examples earlier, we had series, which were like sum of 1 over n squared. So 1 over 1, 1 over 4, 1 over 9, 1 over 16, 1 over 25, and so on. That would be a sequence. And there, the nth term would be 1 over n squared. So there might be a formula like that for the nth term. Or there might be some rule that tells you how to get from one term to the next one. Even if you can't write down a formula for the nth one, there might be some rule like that. But there doesn't have to be. Okay, so a sequence is any list of numbers at all. It doesn't have to be, you know, you don't have to be able to kind of know by looking at it what the 100th term is going to be. Okay, so here are a few examples, and then I'll stop after these few examples, and we'll continue tomorrow. So first of all, if we took, for example, the sequence whose nth term is -1 to the n plus 1. Okay, so it looks a bit complicated, but by trying this out for a few initial values of n, like n equals 1, n equals 2, and so on, we're told that the sequence starts with n equals 1. And then you can figure out sort of quickly what these kind of terms are describing. And it's kind of, I think it's worth practicing because you can, you know, it helps us to not be kind of put off by these kind of descriptions and to figure out easily what they're saying. So the -1 to the n bit is something that you see quite often in sequences and series. And basically what it introduces is a sort of factor that alternates between +1 and -1 as n moves through the integers, because -1 to the n is 1 if n is even, and -1 if n is odd. So here, if we put n equals 1, we get -1 plus 1, which is 0. If we put n equals 2, we get -1 squared plus 1, so that's 1 plus 1. If you put n equals 3, you get -1 cubed plus 1, which is -1 plus 1, so that's 0 again. If you put n equals 4 in here, you get -1 to the 4th, which is 1 plus 1, which is 2. So so even though it's not obvious when you look at this representation of the sequence, the terms of these sequence just alternate between 0 and 2, 0, 2. So it's either, every term is either -1 plus 1 or 1 plus 1, according as n is odd or even. So the sequence just alternates 0, 2, 0, 2, 0, 2, which maybe for a lot of us will probably find that easier to read, but this is kind of a compact description, which describes the entire sequence for us by saying what the nth term is. So I suppose these examples are only kind of about moving between the description of the general term in terms of n and sort of a partial listing of the sequence. It might be useful to us in seeing really what the pattern is, if there is one, and what the terms look like. Okay. Second example, if you look at sine of n times pi over 2, as n runs from 1 to infinity, so we can notice the sine of n times pi over 2 will always either be 1 or minus 1 or 0, according as this n that's multiplying pi over 2 is even or odd. If we have an even multiple of pi over 2, we've got something whose sign is 0, because we're either at minus 1, 0, or 1, 0 on the unit circle. If we take an odd multiple of pi over 2, its sign will be 1. We're up at 0, 1. If the multiple is 1 or 5 or 9 or something that's congruent to 1 modulo 4, if it's 3 or 7 or 11, it's minus 1. So this as n, first of all, as n alternates between odd and even, sine of n pi over 2 moves between 0 and not 0. And for the odd values of n, it moves between 1 and minus 1, starting with 1 when n is 1. Okay, if you put a 1 over n over that, which is the third example here, we get 1, 0, minus 1/3, 0, 1/5, 0, minus 1/7, 0, because every term, the nth term, is being divided by n. So I suppose if you're having a look at these examples before tomorrow, the things to think about are, what are the terms in this sequence doing as n increases? In the first two examples, they just continue alternating between 0 and 2 in the first example. In the second example, between 0 and not 0, but the not 0 part is moving between 1 and minus 1. So the kind of, I suppose, the overall kind of magnitude of the non-zero terms is not changing in this first example. It's always 2. In the second example, again, it's always 1 or minus 1. So they're not converging to anything. They're not getting closer to any particular value. We're going to have a precise meaning for that tomorrow. In the third example, it's similar, but something else is going on as well. In the third example, the zeros are still occurring at every second position. But this introduction of the factor 1 over n means that the absolute value of the terms are also shrinking as we proceed out, because the nth term is being divided by n, so it's bringing it closer to 0. So here we have a sequence that has kind of slightly different behavior. It still has this alternation between 0 and non-zero thing going on. The even terms are all 0, but the non-zero terms are actually, the one that occurs in position n is divided by n. So instead of just being 1 or minus 1, it's being brought closer and closer to 0 as n increases. So this is an example of what they call a convergent series. A convergent sequence. Its terms are kind of converging on 0 as n increases. And okay, kind of converging on 0 is an imprecise phrase, and our first order of business tomorrow would be to make that into a precise phrase in a way that's a bit fussy, but actually quite important, as we'll see. Okay, thank you very much, everybody. That's it for today. I'm going to stop the recording, and thanks very much to everyone who's joined us for the video, and see you tomorrow.